Welcome to this video on Year 1 Rates of Reaction. Rate of reaction can be defined as the change in concentration over time. We can work out units of rate by using the equation rate equals concentration over time and plugging in our units into this equation. So if we use moles per decimeter cubed for concentration and seconds for time, the units of rate will be moles per decimeter cubed per second. If we look at a concentration time graph, we can see that the curve is the steepest at the start. Then it becomes less steep and finally levels off. The rate can be found at a particular time by drawing a tangent to this time and finding the gradient. When the curve is the steepest, the reaction rate is the fastest. But why is this? It's because at the start of a reaction, we have the highest concentration of reactants. As the reaction proceeds, the reaction slows down as reactants start to get used up. In other words, their concentration decreases. This results in less frequent collisions happening. When the curve levels off, this corresponds to when one of the reactants has been completely used up. We can see the concentration is no longer changing. The line is horizontal, and so the rate is 0. You might remember from GCSE the 5 factors that affect rate of reaction. These are temperature, catalyst, surface area, concentration, and pressure. To understand why these affect the rate, we should first look at collision theory. In reality, only a small amount of collisions result in a reaction. Collision theory states that 2 things are needed for a collision to be successful, one that results in a reaction. Firstly, the particles must collide with the correct orientation. So the 2 reactive parts must collide rather than something just bouncing off the end of a molecule. And the second is that the particles must have energy equal to or greater than the activation energy for that reaction. So bearing this in mind, how exactly do those 5 factors affect the rate? This table shown here explains just that. Another thing you need to be aware of are some of the ways that rate of reaction can be monitored through experiment. Any reaction that involves an acid, alkali, oxidizing or reducing agent can be monitored by titration. In this example, we produce an acid, so we can monitor the concentration of this over time and therefore find the rate. In the second example, we are going from a colored substance, iodine, to colorless substances in the products. And in the last 2, we have a reaction that forms a gas. We can either do this reaction in a flask on a mass balance to monitor mass loss, or we can connect the conical flask to a gas syringe and collect that gas and measure volume over time. Volume of gas produced and mass loss are both proportional to change in concentration. So these properties both give a measure of rate of reaction. You need to be able to draw a label diagram to show the equipment setup for gas collection. Take care to ensure that your diagram clearly shows that the conical flask is sealed with a bung and that the delivery tube goes inside the conical flask. The data gained from these experiments can then be used to plot a graph. Graphs of volume or mass versus time are shown here. The rate of reaction can be found at any time by drawing a tangent to the curve at that particular time. The initial rate, which is the rate at time 0, can be found by drawing a tangent to the curve at 0. One way this can be done is by lining your ruler up with the first 2 points on the curve. Finding the gradient of this tangent will give us the value for initial rate. Let's take a look at an exam question that covers a lot of the stuff that you've just seen on this video. The first bit, it says explain why there is a loss in mass during this reaction here. So even though we don't have any state symbols, we can see that we've got carbon dioxide released and we know that is a gas. So we can say because a gas, which is CO2, is released. and that will escape and be lost as mass. The next part is a moles calculation. So we've got a volume and a concentration of the nitric acid. So our first step can be to work out moles of that. We've also got a balanced equation up here. The question's asking about the strontium carbonate. We can see we've got a 1:2 ratio of the carbonate to the acid. So we can use that ratio to work out the moles of the carbonate. And then the final step, we can get the mass of the strontium carbonate by doing moles times mR. If you want to have a go at this one, pause the video here. You should have calculated the mass of the carbonate to be 1.85 grams. For this next part, it says the student plots a graph of mass against time, and these results are from this reaction up here. So the CO2 is lost, it's released, and then we see that decrease in mass over time. So this part is asking us to describe and explain the change in rate during the first 200 seconds, and this next bit is asking us to calculate the rate of reaction at 200 seconds. If you'd like to have a go at these by yourself, pause the video now. So to calculate the rate at 200 seconds, we need to line our ruler up with the curve at 200 seconds. So 200 is here. And then we can draw a tangent to the curve at 200 seconds, turn it into a triangle. We can calculate change in y over change in x. So reading off the scale for this tangent, we get these values, change in y over change in x, and we can work that out, and we get 6 times 10 to the minus 4. So to describe and explain the change in rate during the first 200 seconds, we have to talk about what we see on the graph. So first of all, what happens to the rate? Does it increase? Does it slow down? So the rate of reaction decreases. And we have to say why that is. So that's because the concentration of reactants are decreasing, the reactants are getting used up as the reaction progresses. And how does that affect the rate? Well, that results in less frequent successful collisions. Looking at this last question then, it says outline a method that could be used to obtain the results that are plotted on the graph, include the apparatus and the procedure. It's only 3 marks, so for the procedure we just want something brief. The first marking point then is for listing all the equipment we'd need. So we want something to contain our reaction, like a conical flask or a beaker. We need something to record mass with, so a mass balance. And we can see it's mass against time. We need something to record the time with as well. So a stopwatch, or we can call it a stop clock, or whatever you want to call it, just something that records time. So those 3 things. And for the procedure, we just need to make a couple of comments. So to be honest, all we need to say is that we need to record the mass at regular time intervals. That's the second mark. And for the final mark, we need to quote a sensible time interval. So we don't want anything too frequent, otherwise human reaction time, our reaction delay will, produce an error. Our results won't be too accurate. And we don't want anything too large because it will change a lot in that time and then we'll end up with anomalies on the graph. So the time interval should be between 10 and 50 seconds, ideally something like 20 seconds. Moving on to catalysts then, a catalyst can be defined as a substance that increases the rate of reaction without being used up. It does this by providing an alternative reaction pathway with a lower activation energy. We can see this lowered activation energy visually in these energy profile diagrams for an endothermic and an exothermic reaction. Activation energy, the minimum amount of energy needed to start a reaction, is the difference in energy between the reactants and the top of the activation barrier. It is given the symbol EA. We can see how the activation energy is lowered when we use a catalyst, and we label this EC. There are two different types of catalyst, heterogeneous and homogeneous. Let's look at heterogeneous first. This is when the catalyst is in a different physical state to the reactants. Perhaps the reactants are in the gas phase, whereas the catalyst is a solid. We need to know briefly how a heterogeneous catalyst works. These are surface catalysts. That means the reaction happens on the surface. This visual shows how a heterogeneous catalyst works for a general reaction involving reactants A and B forming a product C. In the first stage, reactant molecules adsorb onto the catalyst surface. Adsorption is the process of the reactants binding or sticking on to the catalyst surface. In the second stage, reaction occurs. This is when reactant bonds break and new product bonds form. And the third stage is called desorption. This is when the product molecules leave the catalyst surface. Two examples of industrial processes that involve heterogeneous catalysts are shown here. Homogeneous catalysts are the other type of catalyst. These are in the same physical state as the reactants. The way these work is by reacting with reactants to form an intermediate, which then breaks down to give the product and regenerate the catalyst. Example reactions include ester formation, where both the reactants and the catalyst are in the liquid phase, and also ozone depletion, where both the catalyst and reactants are in the gas phase. We also need to know why using catalysts can be more sustainable. Since they lower the activation energy, this then allows a process to take place at a lower temperature, lowering the energy requirements and the cost associated with these. If less energy is used, then less fossil fuels are used, reducing emissions of greenhouse gases such as CO2. Moving on to the final part of the rates topic, in gases, solutions and liquids, some particles move slowly with low energy, whereas others move faster with higher energy. Most particles are somewhere in the middle, moving with average speed and energy. This spread of energies is known as the Boltzmann distribution and is represented by this graph. There are several key features that we have to be aware of for a Boltzmann distribution. The first is that the curve starts at 0, 0, the origin. This means that no molecules have zero energy. In other words, all molecules have some energy. The next feature is that the total number of molecules is equal to the area under the curve. And the last feature is that the curve never touches the x-axis, since there is no maximum energy a molecule can have. Some other things to notice is that only the molecules with energy equal to or greater than the activation energy can react. This is a relatively small proportion of the molecules shown here. The peak of the curve represents the most common energy that molecules have, and you'll notice that this isn't enough energy for them to react. Next, we will look at how temperature and use of a catalyst affects the proportion of molecules with enough energy to react. Increasing the temperature shifts the curve to the right. This means that the average energy a molecule has increases. The curve also widens. This means a broader spread of energies result. And the curve also flattens, since the total area under the curve must remain the same, as the number of molecules has not changed. We can see the extra molecules that now have enough energy to react, as indicated by the shaded area here. When we use a catalyst, the curve stays the same, but now we have a new lower activation energy, and we label this EC. And we can now see all the extra molecules that now have enough energy to react. Let's finish with an exam question then. The question says, explain using Boltzmann distributions why increasing the temperature and using a catalyst both increase the reaction rate, and it's worth 5 marks. So even though there's a lot of space for a written answer, we actually only get 1 mark from what we write here. The rest of the 4 marks are for the graphs. So if you'd like to have a go at this question yourself, pause the video here. So to answer this, we draw the 2 graphs that we've just seen in this video. One showing the effect of temperature and the other one showing the effect of using a catalyst. So this one can be the catalyst one, and this one can be the temperature one. And then I'm going to do another curve, also starting from 0, 0, and it's going to shift to the right. It's going to be lower in energy and it's going to be wider. And don't forget, we need to label our axes as well. So here, number of molecules, or we can have number of particles, either's fine. And on this one, energy. Let's do the same here. And this is just an abbreviation for number. And we also need to show our activation barrier. So our activation energy on this temperature one, put it somewhere around here, label it EA. On the catalyst one, we've got our normal activation energy without a catalyst, and we've got our new lower activation energy EC when we do use the catalyst. So the majority of our marks we've already got from these 2 graphs, and then we need to write something further explaining how using these increase the reaction rate. We just need a statement. We can say more molecules, or we could say more particles, or even more collisions have energy equal to or greater than the activation energy. And that by itself might even get us the mark, but I'll just add this next bit on because sometimes they want a little bit more. And this results in more frequent collisions. And let's go with successful collisions because they're the ones that result in a reaction. Let's label which one shows the effect of a catalyst and which one shows the effect of temperature, to show the examiner that we know what we are talking about. And we can even label these curves. This is the higher temperature, and this one was the original temperature or the lower temperature. And there's our answer. Let's have a look at the mark scheme then. So just for drawing the Boltzmann curve, just the shape of the curve itself drawn properly. So it starts 0, 0, it never touches the x-axis. That gets us 1 mark by itself. And the axis titles also get us another mark, so that's 2 marks already. And then for the curve showing the effect of temperature, so that's the one that shifts to the right, it's lower and it's wider, we've already got 3 marks out of 5. The 4th mark then is for that second curve that shows the lowered activation energy when we use the catalyst. And the final mark, the 5th mark, can just be from one sentence in the written answer bit. So you could say something like, more particles or molecules or collisions have energy above or greater than the activation energy. Or there's a bit, I don't know why it's in yellow, but it says, or they have enough energy to overcome the activation energy. So we don't actually need anything about more frequent successful collisions to get the 5th mark in this one. Well, that's the end of the Year 1 Rates of Reaction Complete Topic Revision video. I hope you found that helpful. If you did, please like and subscribe for more similar videos. Thanks for watching. See you again soon. Bye.